ready for takeoff.
Okay, so welcome to my talk, Splitting the Crucial Optimization for Ruby Blocks. I'm Benoit Daloze, and I work on Truffle Ruby since quite a while, actually, since 8 years. I did a PhD on parallelism in concurrent on dynamic languages. I'm the maintainer of RubySpec, and I'm also a CRuby committer. And you can find me on Twitter, Mastodon, and everything. Truffle Ruby is a high-performance Ruby implementation, really aims to be the fastest Ruby out there, and that's a good deal of that is through the JIT compiler, the just-in-time compiler it has, which is the GraalVM just-in-time compiler. And Truffle Ruby targets full compatibility with CRuby 3.1, including C extension. So it really aims to be a drop-in replacement for CRuby. And so, for instance, recently we tried to run Mastodon, which is like a Rails app with a few hundred gems, and actually it just works on Truffle Ruby. There's only like a single line change in the Puma config, but everything just otherwise the server just starts and everything works. It's on GitHub, and there's a website, and so on. So today I want to talk about splitting, but what is splitting? And to explain it, I want to go back to the origin when this concept was actually invented. And that was actually like quite a long time ago. So in 1986, some researcher created the self language. And the self language is a little bit similar to Smalltalk, which is quite similar to Ruby, but it's actually prototype-based, so it's a bit like JavaScript in that aspect. And the self-researcher actually had many breakthroughs, and here I just listed 4 of them. And these breakthroughs, they're all used still in almost all dynamic language implementation nowadays, because they are so important, they're so fundamental to having good performance in dynamic languages. And so one of them, for instance, is the self-maps, or the shapes, which is a way to represent objects efficiently, and that's been used by Truffle Ruby since the beginning, and CRuby just recently, like a few months ago, started to use it too. The another concept they went through is de-optimization. So once we just-in-time compile Ruby code to machine code, sometimes it doesn't hold anymore. Like for instance, somebody after monkey patch some method, then we cannot use this optimized code anyway. So what we do is we have to go back to the interpreter, restore all the state of the interpreter, that's what de-optimization is, and then later we can potentially compile it again. And then a third concept is polymorphic inline caches. And this I will explain as we go through the talk when I have a concrete example. And finally, splitting. That's the subject of this talk. And splitting was invented in this paper 33 years ago. It's called the customization of the splitting paper by Craig Chambers and David Gangar at Stanford. And what's amazing is the example they use in this paper, this, of course, self-code, can be very easily translated to Ruby. And the concept basically hold one-to-one. So we're actually going to take this example and translate it to Ruby. And it's fairly straightforward, because actually, like you might notice, but self also has blocks and has a very similar concept overall. So what they do with this example is it defines a sum2 method. And it defines this on all numbers, so it defines it on numeric. And then it's very simple, right? We say sum equals 0, and then we step from the current number, which is implicit, the self, until the upper bound included, and then every time we just add it to the sum. So it's really a trivial example, but it's a good example to illustrate splitting. And as a note, we use step here, not up to, because up to is actually only defined for integer. It's not defined for float and rational and so on. And this function, you can do you can call it on various things, right? So you can call it on integers. You can do 1 sum to 10, is just 55. You can use floating point numbers. You can use rationals, and you can use large integers, for instance. It just works for all of them. And so we want to make this function fast, right? We want to see, like, OK, how would like an optimizing Ruby implementation go about this? Like, how can we actually optimize this properly? And to do that, we're going to just-in-time compile, or we're going to illustrate how we would just-in-time compile this sum2 method. And the sum2 method doesn't do much, right? Does the sum initialization return sum? That's nothing, that's trivial. The main thing is it calls this step method, right? And the first question is, can we inline step? Can we, when we compile sum2, also compile step within it and optimize them together? And Here, the first approach we take here is can we know that it will call numeric step from a static analysis point of view? And the answer is no. Even though we know self is a numeric, because it's a method defined on numeric, we don't know if somebody might have defined float step or integer step or rational step. And that would then take over. And then it wouldn't call numeric step, so we couldn't just use the logic from numeric step would be incorrect. And here I have two example call sites. I have one sum to 10 and 1.0 sum to 10, 0, just to give an idea of what might be used. So dynamic language implementation, how they deal with this, because static analysis is basically useless in Ruby because we know very, very little from it. What they do is they use inline caches. So it's a cache that's in the representation that the virtual machine uses to execute. So for instance, on Ruby, it's a cache that's directly in the bytecode. That's why it's called inline. It's together with the representation of how we execute things. And Ruby, for instance, will be inside the abstract syntax tree directly. And in this inline cache, for instance, what we want to cache here is method lookup, because method lookup can be quite expensive, right? It can be multiple hash map lookups and so on. We don't want to do that every time. And so we have a cache. And we say, OK, when we have integer and we resolve through method lookup, the result was numeric step. And then when we saw a float from the second example, the result was also a numeric step. And Ruby, we have a slightly more advanced version here, where actually we have two inline caches. So we have the lookup cache, which we just explained, but we also have the call target cache. And the call target cache is simply OK, after we resolved everything, which method did we end up calling? And here, it's always the same method. It's numeric step. And because now we have a single method, we know basically OK, most likely we are going to call numeric step here. It's not a guarantee. It could still change. But so far, it has always been the case. And we're just going to suppose it's going to continue like this, right? And so because we have a single line tree like this, it just makes sense to inline it. Because at that point, you're why not, right? We basically know, or we have a very good guess that it's going to be numeric step. So let's compile numeric step, or let's look into it. The problem is numeric step is really complicated. It doesn't fit on a slide, and this is already a simplified version that doesn't handle keyword arguments and more things. And the reason it's so complicated is because there's many ways you can call numeric step. So you can call just one step to 3. OK, just 1, 2, 3, very easy, right? But you can have that with floats. You can have that with a step value of 2, so only, for instance, only odd numbers. Or you can have -2. You can actually go descending. Or you can use keyword arguments. And if you use keyword arguments, you can even omit the 2 value, so then you step to infinity by the given step. And you can also just call it without a block, and then you get an enumerator. So that's just to illustrate numeric step can do a little bit of everything, and that's why it's quite complicated. But I want this to fit on a slide, so I'm going to simplify a few things. So I'm going to remove this first 3 line, because the first line checks the enumerator case, but we're not really interested in that in this talk. And the other 2 lines just check that the step is not 0 or nil, because that's error cases. So just get rid of this. And then we have the descending and the ascending case, whether the step is positive or negative. The case we are interested to for sum2 is the ascending case. So the descending one, we'll just put it in a different method. We just put it here in step descending to get it out of the way. And now we have something that actually fits on a slide, and we can think about how do we compile this. And the important part in this whole method is the loop, because that's where we're going to spend most of the time. That's where the CPU will be executing this most of the time, and that's typically loops are good places to look for optimization. So we have this loop, and inside this loop, what is there in there? There's just actually value bigger than limit. OK, it's very simple, value plus equal step. But then there's this yield value, right? So we call a block with the given value. And suppose we have 2 call sites again. We have one sum to 10, but we also have a call site directly to step, 1.step3. And that means actually the inline cache will see 2 blocks. It will see the block in sum2, but it will also see the block in main, the one that does pi. And that's the question now. What do we do? Do we want to inline this block too? But which do we inline? So we could inline both blocks. That's a possibility. So we say, OK, if the block is the block in sum2, we're going to do the logic of that block inline. And if it's the other one, we do the other one. And if it's none of these, we do de-opt, which means we de-optimize. So we just don't handle that in the compile code. We'll just recompile again if this happens. But there's a big problem here, because this really hurts optimization. For instance, if it's the first block, and we want here to to actually, we do sum plus equal value, but sum was a variable outside the block. So it means we cannot just access it like this, actually several indirection, right? So that's why I here write it as block.outer variable sum. Like there's at least 2 indirection, right? And this kind of indirection, we want to move this out of the loop, so we can just, we have less work to do in the loop. But we cannot do that here because we don't know which block it will be. And if we do that, basically we would make the second block slower. So that's really the problem here. And then the question is like, what if we don't have 2 blocks, but we have like 7 of them? Then like, sure, we can have 7 cases like this and inline all 7 of them, but that's getting much less reasonable. And now if it's actually the 7 block that's being passed, I will have 7 check until I even get to it. And now it's getting really slow. So that's not good. So what can we do? Well, the idea is very simple. We say, like, what if we copy the method? Here we copy the method step. But like the virtual machine does this, right? So even though I write them step 1 and step 2 here to illustrate, the source code doesn't change. It's the same step we had from the beginning. It's just like the virtual machine is able to optimize all of this automatically. But so the thing it does is it takes a copy of step, and this first copy is going to be specialized for the block in sum2, and the second copy is going to be specialized for the block in main. And then we just have a check, right? Which is like, OK, is it the block we expect to, and otherwise we have to optimize. And so now we can optimize this much better. For instance, this outer variable, we could pull it out and so on. I mean, the just-in-time compiler would be able to do that. So that's cool, and this is splitting. This is very simple. We just copy, basically. So graphically, we had these 2 call sites, right? One sum to 10 and one step to 3. And OK, this one calls sum2, but eventually both call step, and step was calling one of 2 blocks. And I didn't know which one. What we did was just copy step, and now it's much simpler. Now we have like a linear flow here, of course, and that's much more optimizable, right? The CPU is very happy when it has a straight sequence of instruction, and it knows where to go. It's not happy when it has no idea where it is going, and there are many branches everywhere. So yeah, splitting. And so the main advantage is like we take a copy of step here for each caller, and those copies can be optimized further, simply because they have more information. Basically, they have information that, OK, it's only through this caller, so it has less cases. It's more precise. I have the extra context of the caller to optimize it better. And in Ruby specifically, splitting is a bit more advanced than what I explained. But first, I want to define some terms. So we had an inline cache before. An inline cache can either be monomorphic, polymorphic, or megamorphic. And monomorphic means a single entry. That's the happy case. Polymorphic is 2 or more entries. And megamorphic is too many entries. Like when we had 7 blocks, for instance, so on, at some point, we just can't track it anymore. And polymorphic is slower because we can optimize less, but megamorphic is just horribly slow because we cannot cache anymore. So for instance, we would have to do method lookup every single time, right? So we have to say, OK, integer, what's the methods on it? Take a hash map lookup. OK, it's not there. Then we go in numeric. What's the method? Do hash map lookup, and so on. And so what Ruby does is like whenever it detects polymorphism, megamorphism, basically it detects these inline caches are getting 2 or more entries. It tries to split to kind of fix it and be monomorphic again. And in Ruby, we decided to split for each call site once we decided to split a given method. So like once we decided we need to split step, we're going to split every call to step. That's it. But more than that, we can actually split at more level. And I will illustrate that to explain it. So suppose here we have 2 call sites. We have one sum to 10 and 1.0 sum to 10, 0. And so they both call sum2, and then that calls steps. And inside step, I have this loop, right? This until value bigger than limit. Now this bigger than actually is polymorphic. It can either call integer bigger than or float bigger than. That's a problem because like we are in the innermost loop, the most important part of our code, and now we still have to decide between these 2. So we say, OK, we could split step, but if we split step, how does sum2 know which copy to call? It just doesn't, right? So what we do is we split both of them, and then we have this again. And so this is like kind of recursive splitting, and Ruby, for instance, is able to notice this and say, OK, I need to split one level further, and then we can have this, and everything is monomorphic and linear again. And so to make the point again, like what if what if we haven't splitting? What happens? What's the problems, right? And here in red, I put all the places that have polymorphism if we don't have splitting. So for instance, step smaller than 0, maybe step could be a floating point number, and then we don't know. It could be 2 different methods here. This one we saw, and the block could also be different block, and the plus as well, right? So there's already 4 places that are problematic if we don't have splitting. But more than that, if we consider polymorphism as a more general concept, if we consider it for branches, so for instance, if we have an if-else branch, and both are possible, because it's a big program that calls step in many different ways, then basically we will explore all possibilities in this method, and then everything in red here is a place where the CPU doesn't know where to go, where it has to branch, and cannot predict where it goes, because actually all are possible. So that's a big problem, right? And splitting basically solves this by saying we take multiple copies, and then actually we know exactly where we'll go in all cases. So back to having splitting here, we have a sum2 method, right? And now we have actually a split of the sum2 method. And this split is for this call side, 1.sum210. Of course, like this 10 could be like, I don't know, an argument like n coming from somewhere else. It doesn't have to be literal 10. But here, this split, it sees, actually it profiles, so it checks that the argument is always an integer. If it's not, it's deoptimized and recompiles. But here it's most likely that it will always be an integer. So upper bound is profiled as an integer. There's just a quick check, which we don't show. And then after, we can just assume upper bound is going to be an integer inside the method. And so here also in the inline cache of step, we only have 1 and 3. We only ever seen integer as the receiver, so it's simple. So let's inline, let's continue inside step. And inside step, we also have an argument profile. And actually, what arguments did we get? So actually, we had like this upper bound is the limit, and that's the only argument we passed. So limit is an integer, and step is not passed. And that's very interesting. Because step is not passed, we also like profile that it's not passed. So we know that if it's not passed, it must be the default value, and the default value is 1. So at that point, we know that step is 1. So here I highlighted all occurrence of step, and we can just replace them by 1. That's like what the just-in-time compiler would do. And then next thing with, is 1 smaller than 0? Well, obviously that's not true, and the just-in-time compiler can also figure that out. So we can just replace that by false. And then now descending is just false, we can just fold it, right? We can just remove some branches because we know it's not descending, it's ascending. And one more thing here is like we know limit is an integer from the profile, so the or equal it only ever does something if limit would be false or nil, but it's not that, it's always an integer. So this we can just remove as well. Then one more thing we have is we notice that self is an integer. Actually, like I said, we profile arguments, but we also profile self, just because it's useful. And so because we know self is an integer, it means value is an integer. And means value bigger than limit, it means, oh, we actually call integer bigger than. We actually already have this information to an inline cache, but still, like here we can prove it. So even if one less check, we don't need to check that it's an integer, we know it. And then the same thing here for the increment. We know it's integer plus. And we have some checks here that actually we wrote a little bit to fit it on the slide. So it was value, limit, step, any of them float, right? If any of them float, then we have a different logic because you have to be careful. Because when you add float together, if you are not careful, you would just end up with a lot of errors. But so we write this to the original version, which actually is just like a if or, right? And so we have if value is a float, but no, value is an integer, so it's definitely not a float. Or if limit is a float, no, limit is an integer, and 1 is not a float. So all of these are false, so the condition just goes away. It's if false, and so we can just remove it that code. OK, and now we have fairly simple step, like a fairly simple definition of step, optimized one. And now we can inline it, right? So what we do to inline is we just have both methods, and we copy-paste step inside sum2, and we just adjust the variable names. So then we end up with this, right? Now we have the loop from inside step inside sum2. And what we still left here is we have this block, right? This sum plus equal I block, and we still have that there. Then we immediately call it. Well, if we immediately call a block, basically we can understand, like, OK, it's the same as doing the logic inline. So we can just replace it by sum plus equal value. And actually what I'm wanting is like potentially this allocation would stay, but the Graal JIT compiler is able to do escape analysis and realize, OK, nobody used this block, so we can just remove it entirely. There's no allocation either. So it's very as simple as written here. And now we have something that's very well optimized, right? Now we know exactly what it does. It's just a simple loop. There are no calls, except this very trivial arithmetic stuff, which are also like typically also inlined. And now what we have actually is very similar to a corresponding C program, right? So if we look between these two, it's very similar. And actually, the only difference is like the Ruby version does an overflow check whenever it adds something, because we have to care, like, OK, if there would be overflow, we would actually need to use big integers. But this overflow check is pretty cheap because actually it's a flag in the CPU. Whenever you add, it remembers whether there was an overflow, and you can just check it. And there's an instruction to do that efficiently. And so what we did is like, yeah, we have high-level Ruby code with blocks and everything, and compiled as good as C code, basically. But this Ruby code works much better than C code because it works for float, for rational, it doesn't have overflow, and so on. So let's benchmark this, right? So here I have a few call sites to simulate like being in a bigger application, which calls step and sum to in various different ways. And then what I actually benchmark is this, one sum to 1,000. And here I take Ruby 3.1 as the baseline, so it's always 1. And if I use Ruby without splitting, it's already 50 times faster. And the reason for that is Ruby uses an advanced just-in-time compiler, so it's able to be that much faster. But if we use splitting, then we are more than 100 times faster than Ruby. So like we're actually 7.7 times faster than Ruby without splitting. So that's really the benefit of splitting. Like, how can a single optimization make things 7.7 times faster? That's like crazy. It's almost unheard of. And the reason of that is it's a bit like inlining. It's like because splitting triggers, it enables a lot of other optimization to come in. So like it's really an optimization enablers. It enables other optimization to go in, and then we have really big speedups. Like, so instead of having a very generic version which branches everywhere, like when I had all the red on the slide, now it's actually like a perfectly clear version. And so if we take other benchmarks, for instance, if we look at OPT carrot, Ruby without splitting is already 5 times faster, but with splitting, we're actually 7.7 times faster. So here's, again, a big gain from splitting. And that's maybe not so expected on OPT carrot, which maybe doesn't use blocks that much. But still, it uses them to some degree. And then if we look at Rails bench, the version from the Widget bench benchmark suite, we see that Ruby without splitting is 1.36 times as fast as Ruby, which is something. But with splitting, it's 2.75 times faster, and that's much better. So here on Rails, it looks like it's really key to do splitting because it enables so much more optimization. It enables to compile Rails and all the method it uses in a much more efficient way. And to get an idea of the global performance of Ruby here, that's a blog post I did in the beginning of the year. And on the 14 benchmark of Widget bench, we see that Ruby is 6.23 times as fast as 3.1. And so we can think like a big part of this is also splitting. Not only, of course, the better just-in-time compiler also matters, but that's part of the overall results. And we can see Ruby is basically a different level here. Like it has all this very important optimization that so far other Ruby implementations don't really have yet. So I want to talk about some related paper from people at Kent, from Sophie Kaleba, Octave Larose, Stefan Maher, and Richard Jones. And this paper uses Ruby to analyze the behavior of call sites. And so the behavior of call sites, like for instance, are they monomorphic, polymorphic, or megamorphic, but also other things. And in this paper, they find that Ruby has 2 ways to reduce polymorphism and megamorphism. And one of them is 2-level inline cache we saw in the beginning, where we separate the lookup from the dispatch when we call a method. And the other one is splitting. And there's also a blog post on Stefan's website if you want to have a kind of a summary of the paper. And so I took the number from that paper, and specifically the Railsbench number. And we see that initially, Railsbench has about 7% of the call which are polymorphic. That's not good. That's kind of like not so small number of polymorphic call, right? It means like 7% of all calls in that benchmark, actually they don't know where they're going, right? They have to at least choose between 2 or more possibilities. And even more worrying is like 0.5% of those calls, which is still 63,000 calls, are megamorphic, which means they don't have honey cache. They have to do method lookup every single time. But what they see is like after we use this 2-level inline cache for call, this lookup and dispatch cache, we actually reduce the polymorphic call by half. Now we only have 3.5%. And the megamorphic call are now very small, like 0.004%. And then once we apply splitting on top of that, we actually come to a flat zero. There's just no polymorphism, no megamorphism anymore. So that's really a big result, that one that I think they didn't and I didn't expect, is that when you have Rails, you have quite a bit of polymorphism, megamorphism, and actually these two optimizations remove it entirely. And this didn't just happen on Rails bench, but actually happened on all 44 benchmarks in the paper. So in conclusion, we saw that splitting is a technique from the self-VM research. It was invented 33 years ago. But even though it's a bit old like this, it actually applies very well to Ruby. And it applies, for instance, for method taking blocks and calling them in a loop, but not only. There are many more forms of polymorphism, like we saw, like the branches and so on. And we see that splitting can completely remove polymorphism and megamorphism in the 44 benchmark of that paper, which is really quite a good result. And also, it gives really big speed up. Like we see this 7.7 times speed up on Sum2, 1.5 on OPT Carrot, and 2 times on Rails bench. And with that, I want to thank you for listening, and I'm open to any question. Thank you. Right, so the question is, does it have any impact on memory footprint? And yes, it does have an impact, of course. Like if we copy something, we need to use some memory for it. It has an impact which is then proportional to like the representation that the virtual machine uses to represent code, right? So like bytecode or whatever else, right? So it's like, for instance, I don't know, a percentage of that, right? So in Truffle Ruby, there is actually like a limit. It says like, we cannot copy, I think if I remember correctly. So if we take the whole footprint for all the representation of the code for the whole application, we don't grow it up more than 2.5 what it was originally. So we're allowed to split kind of, we're allowed to have one copy and a half, but on average. Some things will never be split, and something will be split many times. But so there's a limit, but actually we don't hit this limit so much. So in practice, like, yes, it needs to be controlled so it doesn't go crazy. But if it's done in a sensible place, it tends to not be too unrealistic. And I think compared to like the application footprint, it's typically not that important. But yes, like every optimization, it's a trade-off. Here's a trade-off of a little bit more footprint for much faster code. Right, so it was this one, right? Yeah. So there's the trick here in Truffle, at least, is that we know, like we notice that step here is called by a single caller. There's only one thing calling step at this point in the program. So this is kind of the first time we see a step being used, right? And that means it's like, well, this can't be the source of polymorphism. Or if it is, we can't do anything about it. So like, let's keep looking higher. And so that we kind of keep looking higher like this, as long as it's single callers, up to a threshold, I think it's something like 5. And then here, for instance, we saw like, OK, now we have 2 callers. We don't have 1, right? So at this point, it's probably OK to split. But even then, if it didn't work, like now we would have a split, but maybe there's still some polymorphism, it would detect it later and then try again to split higher, potentially. OK, then thank you.